In Chapter 11, we're going to take a look at conic sections. Conic sections is talked a little bit about in Algebra 2, and so we're going to continue to talk about it here. Conic sections is basically if you would take two cones, put them point to point like this, all the different shapes you would get if you would cut it are referred to as your conics. You could cut it horizontal here, and you would get a circle. You could cut it at a little bit of an angle, and you would get what we refer to as an ellipse, which is down below. We also have a parabola. So if you cut it at a slightly steeper angle, you get a parabolic shape. It just goes through one of the cones. However, if you cut it so it's pretty much up and down, you get, which on our initial screen here looks like two parabolas, but it's really a different shape than a parabola. It's called a parabolic. It's a parabola. It's a parabolic shape, which are two shapes like this, where on each side it goes out by asymptotes. Now, if you cut it in the exact center, you just get a point. That's referred to as a degenerate conic, along with the last two are degenerate conics. The first four here are your main conics, but the last four or three are the degenerate ones. If you cut it just so it touches the one cone on one edge and touches the other cone on the other edge, you just get one straight line. Or if you cut it so it goes through pretty much up and down so it goes through the middle point here, then you would get a double line. Well, all conics can be written in this form. However, for the most part, we're going to be looking at special forms that the first four will show up in. Here is a way for you to determine if it's in this form here, whether it is an ellipse, circle, parabola, or so on. Basically, you're looking at b squared minus 4ac, which looks like your determinant from your quadratic formula. However, the a is in front of your x squared, the c is in front of your y squared, the b is in front of the xy term. Here's another way of looking at this when you're dealing with a cone. Cutting it like this, you have your parabolic shape. If you cut it pretty much up and down here, you have your hyperbolic shape. Here, if it's cut at an angle, you have your elliptical shape. So we're going to go ahead and take a look at a parabola. We've looked at parabolas before. We've had parabolic shapes that have, for the most part, opened up or opened down. They are always, for the most part, in this form here, when our x was squared. Well, when you're thinking of conic sections, the definition of a parabola in conic sections is a set of all points that are equal distant from your given point, which is your focus here in red, and your directrix, which is this dotted line down here. If you connect all the points that are the same distance away, you will get the parabola shape. Well, this point right here is halfway in between here and here, so that would be there. This point here is 2 units to the right here. Also, you'll notice it's 2 units up from here. Same idea here. 2 units left, 2 units up. If you were to go to this point right here, yes, it's 3 units up, and it's 3 units on the angle right here to get back to your focus. And so if you would go ahead and plot all those points that are equal distant away from your line here, coming straight up, and then going at an angle back to your focus, if you do all those points and connect them, you will get the parabolic shape, or our parabola. Now, a couple of things you need to be aware of. That the length of the latus rectum, that happens to be this green segment here, which goes through the focus, and it's perpendicular to your axis of symmetry. And your axis of symmetry is a line that cuts your parabola in half, so that each side is a mirror image of the other side. Now, the distance from your vertex to your focus, or your vertex to your directrix, we refer to as P, which is 1 over 4a. You're going to need to make sure you know that. Now, parabolas can open up or down or left or right. If it opens up or down, it'll be in this first form here. If it opens it right or left, it'll be in the second form over here. In the first form, if A is positive, it opens up in the positive direction of your y's. If A is negative, it's going to open down in the negative direction of the y's. Similarly, when you're dealing with this over here, it opens left or right. If A is positive, it's going to open in the positive direction of the x's, so that means it's opening to the right if A is positive. However, if A is negative, it's going to open to the negative direction of the x's and open this way. Now, without remembering the stuff that's underlined in red here, you're going to have a hard time doing anything in this section. So make sure you have this stuff underlined in red, highlighted, and refer back to it until you get it memorized. Well, here we have our initial equation. We need to find the vertex, axis of symmetry, focus, direction of opening, our directrix, and the length of the latus rectum. Here's the two basic equations that we need to come up with. We need to take this and put it into one of these two. Question is, which one? Well, you'll notice up here you have a y being squared. Well, which one of these two has a y being squared? Well, it's the one here on the right because you have a y all squared. So in other words, we need to get x by itself. Then we'll have to complete the square to finish getting it in this form. Here's your steps for completing the square. So we're going to take our equation that we have up on top here, get x by itself, which we have down here, and then we're going to complete the square. So to complete the square, you want to group your y's together, which we have right here. Now, when you're completing the square, you don't want to have anything in front of your squared term. So let's take this negative and factor it out of just the y's. So that's what we have right here. The next thing you need to do is to go ahead and complete the square. You need to figure out what number do I have to add here. Remember, you got to take half of your 4 and square it. So you get 2 squared. So we get 2 squared here, but it's really a negative 1 times your 2 squared. So if you add a 2 squared here, you then got to subtract right here afterwards your value of a times what you added here, and that's what we have back here. So what we have in front of our parentheses then would factor into two identical parentheses of a y minus 2 times a y minus 2, which we could write as a y minus 2 all squared. Simplify what's afterwards, and we get this. Your vertex then is always hk. Notice when it's in this form, h is what's afterwards, which is your 3, and k is what's on the inside, which would be your 2. For the most part, it's always going to be the opposite of what's in your parentheses. That's your vertex. Here your a is negative, so you know it's going to open to the left. So you can go ahead and plot your vertex, 3 units over, 2 units up, opening to the left. You could go ahead and use the pattern of the odd numbers of 1, 3, 5. So you could go up 1 over 1, up 1 over 3, up 1 over 5, and same idea here. Down 1 over 1, down 1 over 3, down 1 over 5 to be able to get your points. Or you could go ahead and make yourself a t-chart. Doesn't make a difference. Now when you look at your graph up here, the horizontal line that cuts it in half is your axis of symmetry. So that would be a y equals 2. Then we need to go ahead and find the length of your latus rectum. Remember, the length of your latus rectum is down here in green, 1 over the absolute value of a. A is negative 1, so it would be 1 over negative 1 or negative 1. So then we would get 1 when you do your absolute value.